Yes.
External pumping. Okay, yes. Okay, so how light amplification is achieved? The main process by which we achieve line amplification is shown over here. So suppose we have some system which is energy levels E2 and E1, and there are atoms resting in the energy level E2, and you give another atom over here, and sorry, a signal over here, that is some kind of radiation that passes through a system. Sorry. Okay, my voice is breaking. Is it fine now? Is it
Yes.
all right? Okay. So how light amplification is achieved? Suppose you have a system, you have E2 and E1, there are two energy levels over here, and you have atoms on the upper energy level, and then there is some radiation going through this system, and what this radiation will do, this radiation, seeing this radiation, the atom in the upper system will drop down to the lower lower state, and you'll have an emission of a radiation. So now from one radiation H nu, you have two photons, H nu and H nu. There will be two photons from one. So this is a very simple way of achieving light amplification. So for amplification by stimulated emission. So basically we achieve amplification by stimulated emission. And for stimulated emission, we need external pumping, as Deep Patel has mentioned. So photon induces an atom in the upper energy level to transit to the lower energy level, and as it emits, as it goes down to the lower energy level, it will emit an identical photon, and that photon is identical in terms of frequency, phase, direction, in most of the aspects. So now you have two identical photons, so one photon gets doubled. So that's how you achieve light amplification. So these two photons will now stimulate another two photons to come down to lower energy level, and that will emit two more photons. So now you have four photons. Okay, and this cumulative process goes on, and that's how you achieve amplification when you want to transmit a signal from one end to another end over thousands of kilometers. And this process continues, resulting in the amplification of light. So this is how we achieve light amplification. So now let us try to solve some problem related to light amplification. So as it was already mentioned in the lectures, that for amplification, what do we require? Population inversion, a longer lifetime of the excited state, and low signal to noise ratio at the input and at the output. It should be very low. So because you don't want any noise in your signal which you are receiving. So signal to noise ratio should be low. And longer lifetime of the excited state. Can anyone tell me what does this mean? What do you mean? Why do you need longer lifetime of the excited state? Can anyone answer to this question? Okay, I'll tell you the answer. Why do we need longer lifetime of the excited state? So actually, we already know. It's very logical. So an atom gets pumped to the upper energy level, okay, via some external pumping or via absorption. Now it should stay here until a photon comes and stimulates it or induces it to transit to the lower energy level and emit a photon, another photon which is same as that of the incident photon. Emitted photon should be same as that of the incident photon. So it should stay for the time till this photon is coming. Okay, so that's why we need it for a longer lifetime. We need the atom in the excited energy state to stay for quite a long time. Okay, so that's why you need a longer lifetime of the excited state. So these are the three important conditions to achieve optical amplification. So now, the very first question. Can optical amplification be performed at thermal equilibrium? True or false? So you know how...
False.
Yes, tell me.
False.
False. And why do you say false? What is the reason? You must be having some argument to it, so that optical amplification cannot be performed at thermal equilibrium. What is the reason for this? Okay, I'll tell you the reason for that. What actually happens is, okay, at thermal equilibrium, say at some temperature T, at T, okay, that is in thermal equilibrium. What is happening actually? We have certain probability of atom to occupy these energy states. Suppose I have these energy state E2, E1. So an atom staying in energy state E2, an atom staying at energy E1. These atoms have certain probability, and that probability of occupation of a certain energy level at thermal equilibrium is given by Boltzmann statistics. So what's Boltzmann statistics gives? Boltzmann statistics gives the probability of occupancy of an energy occupancy of an atom in an energy level Em in this manner. Probability of an atom in energy level Em will be given in the following manner. Probability of Em, that atom is staying in an energy level Em, is proportional to, I would say, exponential of minus Em by kBt, where kb is the Boltzmann constant, and here m is first energy level, second energy level, third energy level, and so on. Okay, so this occupation probability actually is exponentially decreasing for higher energy level. This occupation probability is exponentially decreasing, as we see, exponentially decreasing. Okay. So now this is exponentially decreasing as a function of what? As a function of the energy, that is at higher energy levels, as a function of energy, Em. So you have these energy levels. Okay, suppose this is Em, this is some E3, E2, E1. Okay, so now if we plot this probability, occupation probability, that is P of Em, occupation probability, let's say this is occupation probability. If you plot this with respect to the energy level, it will be a decreasing, exponentially decreasing function. It will be something like this. Okay, so this will be E1, E2, E3, and there is some Em. So this is exponentially decreasing. So now for energy states E2 and E1, what will happen? The ratio of N2 by N1 is equal to exponential of, or let's say proportional to, minus of E2 minus E1 by kBt. Okay, so at t equal to 0, what is going to happen? At T Kelvin equal to 0, what's going to happen? At lower temperature, all the atoms will remain in low energy state. Atoms will be in lowest energy state. Okay, all the atoms will stay in the lowest energy state. So what do we have? At thermal equilibrium, in thermal equilibrium, at any temperature, it will require the state with lower energy to be densely populated. That is E2 by E1. Here, if this is N2, this is N1. So, N1. So, the atoms over here in the lowest energy state will be the maximum. This will be less. So, N2 will be less than N1. So, at thermal equilibrium at any temperature, that a state with lower energy will be more densely populated than a state with higher energy. Therefore, N2 by N1 will always be less than unity. Why? Because E2 is greater than E1 at T equal to T greater than 0, and this will mean that optical amplification will not be possible at thermal equilibrium. And so what you need? You need an external pumping source of energy. Okay, so that you can pump the atoms in the lower energy level, this will be E1 actually, in the lower energy level to the higher energy level. Okay, so now based on that, this is my second question. Why is optical amplification not possible at thermal equilibrium? There we answered it false, but we have already answered it in a previous question. Can someone tell me what would be the answer to this question? Will we be able to maintain population inversion for a smaller time? No. Is population inversion easily achieved? No. So is it hard to maintain population inversion? Yes, it's not only hard to maintain, but population inversion will be impossible. So the answer is B, that the to maintain population inversion, we won't be able to do this at thermal equilibrium, and so optical amplification would not be possible. Now, my third question is again very much connected. So, which property of the spontaneously emitted photon differs from a photon that is that is generated by the stimulated emission process in a two-level atomic system? We are considering, for simplicity, I'm considering a two-level atomic system, but actually, in reality, most of our lasers are either three-level atomic system or four-level atomic systems. It's like that. So here, which property will be different for spontaneously emitted photon?
Phase.
Yes, it's the phase. Why? Because what happens is, when we have a spontaneously emitted photon, so these are my energy levels 2 and this is energy level 1. So a photon in the upper state spontaneously emits. Okay, so if it's emitting spontaneously and if I pass on my photon, it won't have the same phase. Okay, because this transition is independent of the number of photons that may be there. This is spontaneous emission. Okay. Now in stimulated emission, what is happening? Stimulated emission, I am stimulating my emission. I am forcing my photon to jump down. I'll pass on to photon and this photon will induce this atom resting in the upper state to transit down and we'll have two photons. So both it forces the atom in the upper state to transit down to emit a exactly clone photon actually. Okay, so photons emitted are in the same phase as that of the incident photon. So for presence of the photon in certain frequency or direction of propagation, polarization will stimulate an emission of a duplicate photon having the same characteristic as that of the original photon. Okay, so phase will not be the same for a spontaneously emitted photon. The phase of the spontaneously emitted photon is different from the phase of the stimulated emitted photon. Now, what can this lead to in an optical amplifier? If in an optical amplifier I have both spontaneous emission and stimulated emission, then what can this lead to? Can someone tell me the answer?
Noise.
Yes, this can lead to noise because now we have two photons of different phase. If in an optical amplifier, I'm writing this down so that for your reference, and I'll share these slides as well. So in an optical amplifier, if we have spontaneous emission, spontaneous emission as well as spontaneous and stimulated emission. Phase will be different. If we have spontaneous and stimulated emission, phase will be different for both. Okay, so if the phase was different for both, then this might lead to some interference process, some destructive interference, constructive interference, depending on the phase difference between the spontaneously and the stimulated emitted photon, and this will lead to noise. Because of these interference processes, there will be noise in my optical amplifier, which is not good. Now, to reduce this noise, we have lot of methods, but we'll come to that later. You have to take separate courses for that. This week we won't do this. So let's now move on to next question. Okay, so next question, match the following. So can anyone tell me what would be the correct answer? How would you match these? Any answer would be fine. You can just have to guess. I can give you a hint. Erbium crystals are three-level systems. You know that, right? So now you can match it. Can you match it now? There is only one three-level system shown in the match the following in column A. B ka 3. 3B. Two options I can see with 3B. A and C. Okay. And what is NDX system? We have another four-level system. NDX solid-state system is a four-level system. So from here only we have only three options. We know about the two options. and we can see it. Nd:YAG is a 4-level system. So C2 is A. So the correct option would be A. Okay. So this is the correct option. What happened? Okay. Yeah, I think it's fine. Okay. So now let's move on to my next question. Next question is about helium neon laser. Can someone tell me what is helium neon laser? A 3-level system or a 4-level system or multi-level system? You had this question in the, you have done week 5 assignment, right? You had this question in week 5 assignment, right?
Yes.
What did you write? Helium neon crystal is a 4-level system. Yes. And what kind of a laser is it? We have different types of laser. We have dye lasers.
Yes.
Sorry?
Yes.
Yes. Helium neon is a gas laser, not a solid state laser. So we have a tube completely evacuated, and we'll have helium neon gas, and this tube will be sealed, and then we'll have these things, these phenomena going on. So can someone tell me what would be the answer to this question? Assertion is a statement which says that in helium neon lasers we can achieve population inversion between two energy levels of neon atoms. All right. But the reason for that they are stating is that because helium atoms have a metastable energy level. Okay, that is also true. But what would be the correct answer to this question? Anyone can answer properly.
B.
B. Yes, that is the right answer. That is, yes. Reason is assertion. The statement is correct. We have a helium neon laser, and lasing takes place between the energy levels of neon atoms. And helium atoms also have a metastable energy state. But actually what is happening, the population inversion is taking place because of collisions between the atoms of the helium gas atoms and the neon gas atoms. So can someone tell me about the working of a helium neon laser? You can unmute yourself. The others can also participate in this. Sandeep, Divya, only Deep is giving all the answer. Muhammad, Tamis, you can also answer. So can you guys tell me how does the helium neon laser work? Like I've told you that we have a gas. It's completely sealed, vacuum sealed in a glass tube. Then what happens? Then what is being done? You must be knowing about the working, right? You must have read about it, and it's there in the textbook as well. If you haven't gone through it, you can refer to the textbook, Fundamentals of Photonics, Sally and Tech. Mostly in chapter 12, I think. Chapter 12 or 13. 13, I think. So any guesses on how helium neon laser works? Divya, can you answer, please? You know how helium neon laser works? And why are we saying that this correct option is B? Why the reason is not the correct reason for assertion? Alright, I'll wait for a few more seconds. Maybe 5 seconds more. Okay, I'll give the answer. So yes. So this is my energy level of a helium neon laser, energy level diagram. So this is the ground state of helium atoms, and this is the ground state of neon atoms. So in short, I'll just say we pass an electric discharge, and this electric discharge will create a plasma. And because of this plasma absorption, collision, and a lot of things will be happening. Because of that, the atoms in the helium gas will go to the excited state of the helium atom. Okay, So now this excited state is a metastable state. That's quite true. So we pass an electric discharge, pump the helium atom to the higher energy state. Then what happened? Helium atoms, there are neon atoms also inside that glass tube. Okay. So in that, what will happen? The helium atoms in the excited state have a lot of energy. So it will collide with the neon atoms that are in the ground state. Now it will send the neon atoms to the ground state, to the higher energy state, that is the excited state, and this will produce the population inversion. And here we have 4 level system, 1 2 3 4. Okay, so this will produce, what will this produce? This will produce my population inversion, and once we generate population inversion and we give a photon, induces to a photon, there will be laser transition or is stimulated emission. Okay, so helium neon laser uses a gaseous mixture of helium and neon. As we see, electric discharge is passed, and this will pump the helium atoms to a higher energy level, which is a metastable state energy level. Then these helium atoms, what they will do, they will excite the neon atoms to a higher level by collision, and this will produce an inversion of population of the neon atom, and this will emit radiation whenever it is stimulated. Now the excited state of the neon atoms are long lived. So for as I said, for releasing for an optical amplifier, optical amplification to happen, we need longer lifetime of the excited state. So neon atoms have also this speciality that the lifetime of the excited states are quite long lived. So then these helium atoms excite the neon atoms to a higher level by collision, and this will produce an inverted population of neon atom which emits radiation, and when they are stimulated they fall to lower levels. So but in this we can have spontaneous emission, we can have some radiation that is non-radiative transition as well. Now about this you might read later, like how this noise can be reduced because of the spontaneous emission of the system. Okay, so now let's move on to the next question. Okay, do you guys know what is the meaning of absorption cross-section and emission cross-section? I have a graph, and the graph says cross-section, and we have these two words over here, absorption and emission cross-section. What is the meaning of absorption and emission cross-section? Okay, from here we see it means area. Basically it has the dimensions of area. Okay, the area across which my absorption or emission is happening, area dimensions, that is length square. Okay, so over here we have absorption and emission cross-section graph, and we have spectral regions. 3 regions are there, A, B and C. What is A, what is B, what is C? So, and which region? Okay. The question says that which region will you choose to achieve high gain? So what could you answer? What do you think could happen, and where will we get high gain? Should it be A or B or C? From the graph itself, can you tell me? Which region should have higher gain, and which region should be used for optical amplification?
C.
C. So someone has also answered over here C. Yes, Sandeep, it is C. You guys are right. So can you give me a reason why it is C? Okay.
From the formula.
It's quite logical. Okay. So I want higher gain. So when will my gain be higher? My gain will be higher when the emission is the most. And when will the emission be most? Emission will be most when the area provided for the emission, that is transition of emission cross section, is the maximum. So from the graph we see that region A, what is happening in region A? We'll just break it into different parts. In region A, we see that the absorption cross section, absorption cross section is greater than the emission cross section. Okay, Now, if absorption cross section sigma A is greater than the sigma E emission cross section, then there will be attenuation. Okay, then there will be what? Attenuation of the signal, because there is more of absorption and less of emission. Okay, now in region B, so what is happening in region A? In region A, there might be an attenuation because absorption cross section is greater than the emission cross section. In region B, what is happening? In region B, sigma A, that is absorption cross section, is equal to sigma E, emission cross section. So here what will happen? Neither attenuation nor gain. Everything will be simple. Whatever signal you sent in, the same signal will, maybe there might be noise loss and everything, will be retrieved back. Okay, but in region C, but that's not the like objective of an optical amplifier. The optical amplifier has to have some gain, then only it will be able to it will be utilized, it will be useful in optical fiber communication system, because without any gain, my signal which I am passing through my fiber is always attenuated. So no gain, no this signal will not be passed through. Whatever we want from the transmission to receiver, the receiving end will receive a very weak signal, very lossy signal. Okay, so now what is happening in region C? In region C, sigma A is less than sigma E. That is, there is more of emission. Okay, and more of emission, that is, there is gain. There is high gain. There is not attenuation. So we will choose region C for my optical amplification purpose in this particular system, whatever is being shown. Okay, so the answer is C. Because for an amplification process, the probability of absorption should be much less than the probability of emission. Okay. Okay, alright, because for an amplification process, the probability of absorption should be much less than the probability of emission. But tell me one thing, if so this will lead to amplification for a longer time or not? So I have these population inversion. I have my system where there is few electrons over here, E2N1, E1N1, E2N2. Tell me one thing, I'll give this as a homework to you. If my probability of absorption is less, probability of emission is more, that means more and more photons are coming down. That's true. But in the long run, if for a longer time, if I want amplification for a longer time, for a greater length, so won't the upper level getting depleted of the atoms? And if the upper level is getting depleted of the atoms and even the absorption is not happening, that is, this atoms are not replenished again, no replenishing, these are not getting replenished, then will this sustain? Will the amplification, optical amplification sustain, or will it decay down with time or with
No.
distance? No. Why?
Gain will reduce.
Yes.
There will
Gain
be
will
saturation.
exactly. There will be saturation till there is some gain saturation. Can someone tell me how the curve with N with or WI look like?
Decreasing.
Decreasing curve. Yes, it's a decreasing curve. So there is some saturation to the gain. Okay, so now let's move on to my next example. Okay, till now how many questions have we done? Okay, we have done 6 questions. Now let us move on to the next example. So here in this example, we have some information given. Okay, we have a ruby laser. They have 2 energy levels, and both the energy levels are separated
Slide
by
is not changed.
huh? Slide is not changed. Is it changed now?
Now it is visible.
Okay, thank you. Thanks for telling me. Just a second. I'm changing in your. No, it's fine. All good. So I've been given some information about what? Okay. I've been given some information about the ruby laser, and this ruby crystal have two energy levels, and they are separated by an energy difference that is corresponding to free space wavelength. So my wavelength is given, okay, and spontaneous lifetime is also given. That is, after how much time will the electron in the upper energy level spontaneously decay back to the lower energy level. That is 3 milliseconds. It's given. Refractive index of ruby is also given, though I don't think so this will be required, but let's see. And total ion density, that is total population, is also given, 10 to the power 22. Transition line width is given 330 gigahertz, that is delta of V, and this transition line width can be related to line shape function. Now here I would like to ask you a question. What is the meaning of this transition line width and the line shape function? What do you understand by this? Others also please participate in the discussion. It will be good for you. What is transition line shape? What do you mean by that? Then only you'll be able to, if your concepts of these things are clear, then only you'll be able to solve this problem, right? What is I'll wait for say few seconds. Let's say 10 seconds. Someone can answer in that. Please answer. What is the meaning of transition line shape? And since it's an
It is
online
the
discussion.
frequency of a particular substance.
Sorry. So can you say that again?
It is the frequency of substance.
Okay, your voice was breaking. My internet connection might not be good. Maybe that's why. You're taking. Can you please write it down? I was not able to hear it properly. So, okay, I think you must have said the right answer, because you're talking about for particular frequency, right? For there's a spread in the frequency. That's what you're talking about?
Yes.
Yes. So basically what happens, we have energy levels. Okay. Says this is some energy state E. Now, every energy level had some finite lifetime. Every energy state, this energy state will have some finite lifetime. That you agree. Okay? Now, due to due to this lifetime, each state will also have a finite width. Okay? There will be a finite width that is known as delta E. So this will, what does this imply? This implies that the atom can absorb or emit radiation over a range of frequencies, and that range of frequency is very small. It is this delta nu. Okay, atom absorbs, and because of the finite width, that is finite width I should write, of this energy state E, the atom can absorb, okay, atom can absorb or emit radiation over a range of frequency. Okay, over a range of frequency. And this frequency is known as delta nu. Okay, this range is very small than this E or omega or delta or nu. This is very small range. I'll write in bracket, this range is a small range. Okay, so whenever a radiation is incident, then the strength of interaction of this energy state with the radiation is a function of frequency. Strength of interaction of radiation with frequency. strength of interaction of radiation is a function of frequency. Okay, it's a function of frequency. With radiation is a function of frequency. This strength is a function of frequency. Okay, and this function of frequency is called the line shape function, and this function of frequency is known as the line shape function. So it has some particular full width half maxima, and that full width half maximum, that is transition line width, is delta nu, line shape function. Okay, and this line shape function is represented by this g of nu. Okay, and this g of nu is equal to, as being given in the hint, 2 by pi delta nu. Okay, you should do one thing for the theory of line shape function. If everyone wants to understand it in a much better manner, where you have line shape related to this delta nu, or line shape is also related to the transition cross section, that is emission and the absorption cross section. For this, a very beautiful theory is given in the book Saleh and Tech in chapter number 12. So you should refer to that. Okay, and if you have any doubts, come back to me regarding those doubts. Okay, so I have been given a lot of information at spontaneous time. I have given information about how much is the population and how much is the width of the state. That is a transition line width, 330 gigahertz. And also I have been given about the energy level, energy difference between the level in the terms of wavelength. So from this we can find the energy difference in terms, from the wavelength we can find the energy in joules or electron volts. Okay, so what is the question? I have to find the absorption coefficient. Okay, what do we have to find? We have to find the absorption coefficient, that is alpha of nu zero under the conditions of thermal equilibrium. So mind it, whenever you see thermal equilibrium, Boltzmann distribution will be obeyed. Here we have given a hint that assume Boltzmann distribution is obeyed, and I have been given the temperature as well, so I can find N2 by N1, but my N is already given. So at thermal equilibrium I can assume that this N is equal to N1, that is most atoms are at lower energy level, lowest energy level. Okay, because it's in thermal equilibrium and Boltzmann statistics is followed. Okay, so now let's move on. What are we supposed to find? Absorption coefficient. So how do we find absorption coefficient? Absorption coefficient is related to the how much atoms are there in the lowest energy level, okay, into the absorption cross section. That will give me absorption coefficient. So for that we need to find, we already have N because my this thing was given, the concentration was given, population was given, and we have been told it's a at thermal equilibrium. So we know how much population is there in the lowest energy level. So now we have to calculate absorption cross section. For this, absorption cross section is actually dependent on the wavelength of the emitted light, the spontaneous lifetime, and also on the line shape function. So this is the formula for the absorption coefficient, and here we do some calculations and we find that this is equal to 31 dB per centimeter. Okay, will you get in dBs by finding this N1 into sigma of nu zero? You won't get the answer in dB. No, you won't get it in dBs. You'll have to convert that in dBs. Okay, how do you convert it in dBs?
10 log into gain.
Gain coefficient, right? Okay, just you'll get this. To convert in dB, you know the how to convert in dB. To convert in dB, just take 10 log of whatever the gain coefficient you get. Okay, is that all right? Any confusions, any questions related to this question? Because it's a connected question. The next question will be dependent on these answers. Okay, I'll move forward. Okay, now can anyone answer this? The population difference n to achieve a gain coefficient of gamma of nu 0. How to achieve this? Okay, I'll tell you the answer. So I have to find the population difference n to achieve a gain coefficient. For that, what are we supposed to do? We know that is we are being given a gain coefficient, and we have used this formula before, that n into whatever be the absorption cross section, okay, is equal to my coefficient. There we found the absorption coefficient because we were using absorption cross section. Now here we will use a gain coefficient. My gain coefficient is already given, and it's not in dBs, it's already in per centimeter, so no need to convert it. Okay, and we are being given the absorption cross section. We can use the previous cross section because here maybe we are referring to absorption cross section is equal to the just a second, absorption cross section is equal to the emission cross section. Is it being mentioned anywhere? No. But we don't have any other information to find the emission cross section. So we will assume that the absorption cross section is equal to the emission cross section. So we have a gain. So from there we can find so from there we can find this gain coefficient is gamma of nu 0 divided by your whatever the absorption cross section you got. Okay, so this would be the gain. Okay, now next let's move on to the next answer. Do confirm the numerical values of the question. Okay, because I have calculated in different calculators and different mathematical apps like MATLAB and all. So I was getting different answers. Just confirm the calculations, and if there is any discrepancy, just let me know. Okay. That's why we give in our answers, our solutions, we give a range of answers that the answer is correct from this range to this range. Okay, we have been given the length of the medium. No, we have to find the length of the medium. And we have been given the overall gain. So how to solve this? 3 dB. We have been given the gain coefficient. We have been given the overall gain also. Now how do we find this? But now we have to, now no population and all. We have to relate the gain and the gain coefficient with the length. Yeah, does anyone know the formula related to that? How much is gain in terms of? Gain in terms of gain coefficient and the length. What is the formula for that?
Exponential of gain coefficient into length.
Yes, that is the formula. Okay, so gain is equal to exponential of whatever the gain coefficient we have into the length. Okay, now we have that gain is equal to 3 dB, so you have to convert it, is equal to 10 log of whatever gain we have. Now here from by converting it you will get the gain, and that gain is actually is equal to, how much is that gain? Anti-log of how much? Tell me. 0.3. Yeah, anti-log of 0.3. So now you get the gain over here, and so that will be equal to what am I doing? Yeah, I'm doing it correct. So anti-log of 0.3 is equal to exponential of gamma of d. So again you have to take log of this. Okay, or you already calculate anti-log of 0.3, that will be around 1.99 is equal to exponential of gamma of d. Now take the reverse exponential and just find the gain. That will be ln of this, ln of 1.9 divided by what? The gain coefficient, which has already been given. That will give you the answer of the length. So, and that length is around 0.98 centimeters. Okay. So now the next question. How do you find the relative population? How to do this sum? It's a very easy sum. We have been doing this since the very beginning of our class. What do we need? What is the keyword over here?
Boltzmann statistics.
Yes, we'll be using Boltzmann statistics to find out the relative population. Relative population, that means you have to find the ratio of N2 by N1.
But
And
here they have used N1 by N2. Answer is A.
oh, you're right. Correct. This will be N1 by N2. I have written it wrong. Okay, answer is right. It will be N1 by N2. I'm sorry. That will be exponential of E1. Just confirm with the calculation. The whole concept is you have to use Boltzmann distribution. This is the actual concept. I might have made mistake in the signs and also in some calculation. Just
No, it's actually N2 by N1 only, but uh, they have used, I don't know, there is some confusion. In the graded assignment also there is two questions where uh, this formula's answer does not match with the data given.
okay. Which are the two questions? I'll look into it
8
quickly.
and 9. If we use N2 by N1, then the answer is match with the question number 8, but not with question number 9.
8 and 9. Oh, okay, I
There are
should
sub
have.
questions of a single question.
My 8 in the graded assignment or non-graded assignment.
Graded
Okay, it's in graded assignment. This is assignment 4 or assignment 5?
5. The
Okay.
question is calculate the ratio of spontaneous emission rate to the stimulated emission rate.
Are you sure this is graded assignment 5? I think this is grade
5, big 5.
8 and 9 question. This was, I think, question number 2.
No, this was question number 3 of practice assignment, week 5.
Okay, this was a practice assignment.
This question was of practice assignment, yes.
Okay, practice assignment of week 5.
Yes.
Okay, I'll look into it. Practice assignment week 5, question number 8 and 9, right?
No,
Then,
the question which you solve is of practice assignment, and on which I am talking about is of graded assignment.
okay, okay. Okay, just write this in discussion forum. I'm getting a bit confused between practice and graded assignment week 5 or week 4.
And also there is a correction in week 4 assignment. Uh, I mentioned